Hello, Mario! In this video, I'm going to be calculating some batter slopes. And here's the first problem that we're going to look at. It's proposed to raise the existing orange embankment up 2.8 meters. And the slope of the orange embankment is currently 1.3 or 1 to 3 at the moment. That's 1 vertical to 3 horizontal, and the additional bit that we're going to up, we've decided that it's possible that we can put that at a steeper slope of 1 to 2. So what we need to calculate is x and y. We just need to know how far down the existing slope we're going to, where the toe of the new batter will be. And yeah, just how far down and out there, x and y. So this is a fairly little elegant solution to this problem. So we can see here that x, because the slope is 1 and 3, x here will equal 3 times y. Okay, because that's the vertical component, so the horizontal component will equal 3 times the vertical, and that's using the 1 to 3. Now with the 1 to 2 slope, we can see that x there, the horizontal component, will equal 2 times the vertical component, which is y plus 2.8, or 2.8 plus y, as I've written it here. So x in both cases is the same, it's the same x, so therefore we can say 3y equals 2 times 2.8 is 5.6 plus 2 times y, 2y. And then change the sign, we get 3y minus 2y equals 5.6, y equals 5.6. There we go, that's y done. Now we know that x equals 3y, and x, that is 3 times 5.6, so x equals 6.8. QED, quite easily done. Alright, let's have a look at another one. In this one here, it is proposed to fill an existing bunker, the orange line, to a height of 2.8 above the toe of the existing 1 vertical to 6 horizontal batter there, 1 to 6, and construct a 1 vertical to 2 horizontal, the green batter there, at that same 2.8 to that existing ground, and that will create a little water table drain situation there. And once again, we need to know or calculate x and y. So very similar again here, that we know that y by 2, y being the horizontal component, if we divide that by 2, that will give us the vertical component there, and that y over 2 plus y over 6, so here we've got that little bit there actually, and y over 6, that will equal 2.8. So y over 2 plus y over 6. So y over 2, y divided by 2 will be this little bit here, or x actually. X equals y over 2, obviously there. And this little bit here, which is unlabelled, which is y over 6, those two added together will equal to 2.8. So we've got two fractions here, add the fractions, so we choose the common denominator, 6, 2 goes into 6 3 times y, 3y, 6 goes into 6 once times y equals 2.8, and there we can see that then we can multiply both sides by the common denominator 6, and we get 4y equals 2.8 times 6. So y equals 2.8 times 6 over 4. I always leave things right to the end to do the calculation, because that maintains accuracy, and in this case it works out quite simple, because 4 into 2.8 is 0.7, 4 sevens are 28, so 0.7 times 6 is 4.2, so we don't need to use a calculator or anything like that, just our straight out times tables and stuff like that. And there you are, we have y equals 4.2, so that would give you an idea of the width of that side of the drain. We don't quite know the width of that side. We could work that out fairly easily. Now let's have a look at x. Well, x just equals y over 2. So we know that y is 4.2, so x equals 4.2 over 2, and x equals 2.1. So there you are, some quite elegant solutions to some BATTER problems that aren't that obvious to start with, but nonetheless a bit of a starting point when you're looking with BATTERs and wanting to work these things out. So there you go, calculating some BATTER slopes.